Okay, it's extremely likely that you are trying to remember how to do algebra. So let's do, and particularly in complex numbers that can make for a lot of mess. So let's do a couple of quick problems just to sharpen up our tools on the algebra front, but also to get some of the weirdness of how I works, because it's something that is both involved in sign, addition, multiplication, and also has this funny role inside of the e to the I theta of the Euler relation. So let's think that all through. Okay, cool. Here's a funny one. 1 over I equals minus I. That makes virtually no sense. It looks like division by I is the same as multiplying by minus I. That's one of the funny things about I. So how are some of the ways we could prove that? Well, we could multiply both sides of this equation by I. What do we get? Well, we get I over I, which of course is just equal to 1 on this side. And here we get that equals minus I times I. I times I is minus 1, which also equals 1. Okay, maybe not so strange. What about if we multiply instead both sides by, if we add to both sides I, what do we get? Well, if we add I to this side, we get 0. What happens if we add I to this side? We get 1 over I plus I. Now we want to combine these two, so I need to put an I in the denominator over here, so that's equal to 1 over I plus I over I, and I need another I upstairs to put one downstairs, so I now have I squared in the top over I, which is equal to 1 over I minus 1 over I, also equal to 0. Okay, prove two different ways. Okay, for our next little puzzle, I'm drawing the complex plane to get us back into squared root away with that. This is sometimes said to be the most amazing formula in mathematics. It's actually a pretty amazing formula because it involves all the crazy things that we're supposed to know all together in one formula. Here's 0, which is the addition identity. Anything plus 0 is equal to itself. Here's 1, which is the multiplicative identity. Anything times 1 is equal to itself. Here's I, the square root of minus 1, which is a crazy thing we've been talking about all week. Here's pi, which is, the transcendental number, that has everything to do with the relationship between the radius and the circumference of a circle. Here is E, the Euler Constant, which is the thing that is in that magical e to the x, who has its derivative is equal to e to the x. It's the special number there. It gives just the right amount of exponential to have it be equal to its own rate of change at every x. Okay. An amazing thing that they're all together like this. How can we prove it? We can prove it two different ways pretty quickly. First of all, e to the I pi, we can just use our cosine, our Euler's theorem, and that is cosine of pi plus I times sine of pi. So cosine of pi, cosine of 0 is 1, and it starts out at 1, and then it drops down, and it goes to minus 1 at halfway to 2 pi. So cosine of pi is minus 1. Sine of pi, sine starts out at 0, goes up to 1 at pi over 2, comes back down to 0 at pi. This is 0 plus 0. That's this part of the equation. So now we need to add another 1. Minus 1 and the 1 cancel, and yes, indeed, it does equal to 0. What does it look like on the complex plane? We start out here. Remember, we're imagining our circle. Our circle has a radius of 1 for e to the I pi to think about it. So we're on a circle that's a radius of 1, like this. That's 1. Where are we? Well, our angle that we're considering here is pi. So if this is the angle 0, this is the angle pi over 2, this is the angle pi. So here is e to the I pi, which is equal to minus 1 plus 1 equals 0. And now for our last little fancy example, we have 1 over 1 plus I. some people really don't like to have complex numbers in the denominator of a ratio of a fraction like this. It's a little confusing because you can't read, like, you know, as we said with the 1 over I was equal to minus I, there's some craziness. You can't easily pull the angle out of this, or what R is out of this, or e to the I theta. So perhaps it is more comfortable to get this complex number up into the numerator, and then we could have it so that we could pull out the real part and the imaginary part. You can't easily tell what the real and imaginary part are here because it's in the denominator. So how do we do that? Well, we do one of the most important tricks for complex manipulation. We multiply by a fancy kind of 1. We're going to multiply by something over something, same something in the top and the bottom, but it's something over something that's going to make the denominator of the product of those two real. What's a thing that's going to make both this times something real? Well, we already know that if you multiply a number, complex number times its complex conjugate, you get its radius on the complex plane squared. That is a real number back. So what if we multiply by the complex conjugate of 1 plus I, top and bottom, fancy kind of 1, 1 minus I divided by 1 minus I. Is that still equal to 1? Yes, it is. It's the same thing over itself. And what do we get when we multiply this through? Well, down here we get 1 squared plus 1 squared. And then the cross terms, the i's plus I minus I cancel out. So we get 1 squared minus I squared, or 1 squared plus 1 squared, which is just 2. And what do we get in the upstairs? We get 1 minus I over 2. And maybe that seems a little bit weird to you because it's got something that's a 2, and there were only 1's and i's over here in the downstairs, but here it's got a 1 and a minus I. It's a little bit strange. Maybe we should do something to check that we got the right answer. Well, what could we do? Well, we could instead multiply 1 over 1 plus I, which is the original thing we got, times the reciprocal of that, 2 over 1 minus I. What do we get downstairs? We get 1 squared minus I squared. 1 squared minus I squared. Let's write that out. 2 over 1 squared minus I squared, which is just 2 over 1 plus 1, which equals 1. So it's the same thing minus its reciprocal. What if we subtract these two things and do a little bit more algebra that way to see whether we get 0? What happens if we do that? 1 minus I over 2. Okay, this should be equal to 0. It's this minus this. Okay, what do we have to do to get there? Well, we need to multiply. We need to come to a common denominator in order to add them together. So we need to multiply this one times 1 plus I over 1 plus I, right? And this one times 2 over 2. Everybody with me? And what does that give me? This one gives me 2 over 2. 2 over 2 plus 2I. That's this one. Minus 1 squared minus I squared, 1 squared minus I squared over 2 plus 2I. 1 squared minus I squared, once again, is equal to 2, so that's equal to 0. All right, that's a little bit of rehearsal on our algebra and things that you might have forgotten.